Good evening. This PowerPoint is going to cover the 4 different naming systems that we will be using in AP Chemistry this year. We are going to begin our presentation on how to determine proper formulas for ionic compounds. The first step is to identify the proper cations and anions. Cations are positively charged ions and the anion is the negatively charged ion. The second step is to balance the charges between the cation and anion. Remember, charges are simply the number of electrons that are lost or gained. So when a compound is formed, it is making the number of electrons lost equaling the number of electrons gained. Lastly, write the number of atoms of each element or ion required to balance the charges. The cation is represented first and the anion is second. We will now work through a few example problems. Remember, you must use your periodic table to determine each element's charge. The first element is potassium, which is a group 1 metal with a +1 charge. And sulfur is a group 16 nonmetal, therefore it will have a 2- charge. So the first method that we're going to use is called the lowest common multiple method. I'm going to show you multiple methods that you can use throughout. You can choose whichever one you'd like. It doesn't really matter to me. For this lowest common multiple method, what you want to do is find the smallest whole number that both ions can be multiplied into, and the number of atoms for that ion is how many times it must be multiplied to equal that number. So in this case, because we have a +1 and a 2- charge, 2 is the lowest common multiple, so I would need 2 atoms of potassium for every 1 atom of sulfur. The second method is just a little bit more visual way to represent the same information. In this case, I'm going to take and add 2 different potassium ions for the 1 sulfur. The total charge that we have for the potassium would be 2+. The total for the sulfur would be 2-, so they add up to equal 0. So your formula in this case would be K2S. For this next example, writing a formula for iron 3 chloride, we're going to use the CDR method. CDR stands for cross, drop, and reduce. So we want to cross the charges, drop the sign, and then reduce if necessary. So if you have a +2 and a -4, you'd want to reduce down to 1 and 2. You can only reduce the charges for a particular ion. Now, in this first example here, we know that Fe has a charge of 3+. The chloride ion has a charge of 1-. So we're going to take those charges and cross them over, and that will give us FeCl3. In this case, because it's 1 and 3, there is no reducing that is needed, and so that will be our final formula. We are now going to work through a few more example problems. If you remember how to do this from last year, please feel free to skip ahead. When you're creating a compound that contains a polyatomic ion, please remember that only the charges can be reduced. If more than one of the polyatomic ion is needed to balance the charge, place the ion in parentheses to show that all atoms are being multiplied by a specific number. So for this first example, we have calcium with a 2+ charge, and we have the oxide ion O2-. So since I have Ca2+ and O2-, you'll notice that both of the charges are equal and opposite for their numerical value, so we only need 1 atom of each. So the chemical formula would be CaO. In our second example, we have iron 2, the Fe2+, forming a compound with the O2- once again. So in this case, once more, you'll also notice that we have an equal ratio for the electrons being lost and gained. So it will also have a chemical formula just of FeO. Now, when we get to our third example in this first row, we have aluminum with a 3+ charge. We have oxygen with a 2- charge. In this case, the lowest common multiple between 3 and 2 is 6. So therefore, I would need to have 2 atoms of aluminum. And to get to 6-, I would need to have 3 atoms of oxygen. So now when we move on to the next row, This will be our first example of a polyatomic ion. So again, I have 1 atom of nitrogen for 3 atoms of oxygen, and together they have a 1 minus charge. So when I look at sodium with a 1 plus charge and nitrate with a 1 minus charge, equal and opposite, so I have a chemical formula of just NaNO3. For our second example, we have calcium with a 2 plus charge and nitrate with a 1 minus charge. So again, lowest common multiple is 2, so I will have Ca, but now because I need to have 2 of the nitrates, I'll put the NO3 in parentheses and I'll add a 2 on the outside. We come to our third example in this row, Fe 2 plus NO3 minus. Again, 2 is the lowest common multiple, so I'll also have FeNO3 parentheses 2. And finally, in that row we have aluminum 3 plus, nitrate 1 minus, so that will give us a chemical formula of AlNO3 parentheses 3. For our third row, where we have Na, once again with a plus 1 charge, and now the sulfate ion, with a 2 minus charge. 2 is the lowest common multiple, so in this case now I need 2 of the sodiums for every 1 of the sulfates. Please notice when I only need 1 of the polyatomic ion, I do not put it in parentheses. That would be considered wrong. For our next example, let's start over here. We have calcium and sulfate. And for this case, we have a 2 plus and a 2 minus, so I only need 1 of each ion. So I have CaSO4. For our next example, Fe 2 plus, SO4 2 minus. Once more, we have a 1-to-1 ratio, so I need 1 atom or ion of each. FeSO4. And lastly, we have Al 3 plus along with SO4 2 minus. So our formula for aluminum sulfate, the lowest common multiple would be 6. So I need 2 aluminums using parentheses 3 SO4s. And now finally we have arsenate for our last anion. So Na plus along with ASO4 3 minus. Lowest common multiple is 3, so therefore I would need 3 sodiums and just 1 arsenate ion. For our next example, Ca2 plus, ASO4 3 minus. Sorry, there's a lot of lag on my pen here. So in this case, lowest common multiple is 6, so I need to have 3 calciums using parentheses ASO4 2. For our third example, Fe2 plus, along with ASO4 3 minus. So that will give us, again, lowest common multiple of 6. So I'm going to use 3 irons and 2 arsenates. And finally, we have aluminum with a 3 plus charge and arsenate with a 3 minus. So I have 3 plus, 3 minus. They both cancel out, so I just need 1 of each. Next, we will begin to name compounds. There are different kinds of compounds that depend on the elements present within them. Each has a different naming system. The first group that we will look at are binary compounds. These can be either ionic, covalent, or an acid. Binary ionic compounds are composed of just two elements, a metal and a nonmetal. There can be more than two atoms because that can balance the charge. Binary covalent compounds are two nonmetals that share electrons. There are no charges involved in covalent compounds. The rules for naming binary ionic compounds are as follows. The metal always comes first in the name while the nonmetal comes last. The ionic compound name can be different based on its location on the periodic table. Metals found in groups 1, 2, or 3, as well as zinc, silver, or cadmium, do not require Roman numerals to designate the ion's charge. These are called type 1 ionic compounds. For these compounds, simply list the metal's name, then write the name of the nonmetal, drop its ending, and add IDE. You can see in this example problem we have aluminum, which is found in group 3, being combined with chloride ion, which is found in the group 17 or 7 depending on the periodic table, and so the compound would simply be called aluminum chloride. So now let's take a look at a few examples. The first one that we'll do is NaCl. So in this example, the metal is sodium, and our nonmetal is chloride. So we would drop the ending for chlorine and simply add IDE. So when we put those two together, we would have sodium chloride. Our next example will be CaI2. For CaI2, our metal would be calcium, and found in group 2. And the I2, we have iodine, which will now become iodide. So for this example, we would simply have calcium iodide. And in our last example, we're going to do Al2O3. Our metal in this case is aluminum. O3 would simply be oxide. So now, as we put those together, we would end with aluminum oxide. For type 2 ionic compounds, the metal is now coming from a non-group 1, 2, or 3. And again, when we say group 3, it's group 13 on the modern periodic tables. These metals can have more than one charge, so we must use Roman numerals to identify which charge is present in the compound. An alternative method that you learned last year is to use Latin names with changing the endings to show the same charges. But luckily, you don't have to do this in AP Chemistry, so we won't focus on that. The only thing that changes for these types of compounds is you must include Roman numerals in the name of the compound. If you look in this example where we have iron combining with chloride, iron is a transition metal that has two possible charges. It can be found as either an Fe2+ or an Fe3+. So when it forms a compound, FeCl2, that would be called iron, Roman numeral 2, chloride. When we have Fe3+ combining with the Cl-, now that would give us FeCl3, and we would name this iron, Roman numeral 3, chloride instead. So this allows us to tell which one of the two ions is present for a metal. So now let's look at a couple of examples for naming type 2 compounds. For this first example, we're going to use CuBr. Now, this is one of those areas where using that second method will help you because you need to determine the charge for the metal. So in this case, knowing that bromine is located in group 17, we know that the bromine will have a -1 charge. So in this first example, knowing that Br is 1-, and we have a 1-to-1 ratio, that tells us that the copper will be a +1 charge. So in this case, for naming, we would say copper, we have a Roman numeral of 1, and then we take the root brom and add the IDE. So the name of this compound would be copper, Roman numeral 1, bromide. Now, like I said, using the Latin names, you had either an us or an ic. Just for review, the us would be the lower of the two charges for the metal. So the copper 1 would get the OUS ending, the copper 2 would get the IC. So an old way of naming this, we would call the first compound cuprous bromide. For our second example, now because I have 2 Br minuses, that tells us that I have a total of 2 minus. We only have 1 atom of copper, so in order to balance out that charge, to have it add up to equal 0, I know the copper must be 2 plus. So in this case, I would still go with the copper, and then I would use the Roman numeral 2, and then I would have bromide. Now, if I were going to do this from the Latin, copper is cupric for the Cu2 plus, and I would have the bromide. So for the Latin naming, it would be cupric. For the non-Latin naming or the systemic naming, we would have copper 2 bromide. Okay, so next we'll be looking at how to name a covalent compound. The first thing, again, covalent compounds are formed between 2 nonmetals, so we're looking at both elements being found on the right side of the stair-step line on the periodic table. With these, again, they are sharing electrons, so there are no charges. When we write them, you just simply say the name of the element that was listed first in the compound and write its full name. The second element, just like the ionic compounds, we're going to drop its ending and add IDE. And then we use prefixes to tell how many atoms of each element are found in the compound. The prefix mono is never used for naming the first element, such as carbon dioxide. We don't say monocarbon dioxide. Here's a list of the prefixes that we will use to name covalent compounds, going from 1 to 20. Typically, most of our covalent compounds will stop at 10. So we look at a few examples to make sure that you understand how to do this. Let's start off with N2O4. So in this case, again, we have 2 and 4 for our number of atoms. Notice in this case, we are not reducing the numbers down to 1 and 2. So in this case, I have nitrogen, and since it has a 2 for a prefix, I'm going to start off by putting a di in front. And now the prefix for 4 is tetra. Since it's a vowel to start off with, at least the O, you can leave off the A from the tetra and just add the oxide. So I'd have dinitrogen tetroxide. If it's an I, such as iodine, then you would go ahead and keep whatever the vowel is for the prefix as well. So you would have pentaiodide, for example. Okay, so let's try one more really quickly. So if we have, say, PCl3, I have phosphorus here. Again, since it is just a 1 for its number of atoms, we don't have to say mono because it's the first element. So I'd have phosphorus, and then I have chloride, and I would add the tri in front. Okay, so we have phosphorus trichloride. And then finally, one last one. If we had something like, say, N2S, now in this case, I would have dinitrogen. But then because the sulfur has only 1 atom, and it's the second element, I'm going to use the mono prefix, and then I would add sulfide, changing the ending to IDE to finish the name. Perhaps the most difficult part of naming compounds is trying to determine which type of compound you have. So for your binary compounds, the very first thing that you want to look at is whether or not a metal is present. Both ionic and covalent compounds will have nonmetals, but the first element for an ionic compound will always be a metal. So once you have determined whether or not you have a metal present, if you have no metal present, then you know that you have a covalent compound, and therefore you should just use prefixes to tell how many atoms you have of each element. If there is a metal present, now you have to look where's the metal located. So again, for those type 1 metals, remember that's where you're looking for groups 1, 2, or 13, silver, zinc, or cadmium. All of those do not need Roman numerals. If it's any other metal located in a group that is not 1, 2, or 13, then you need to determine the charge of the cation and list the charge using the Roman numerals. Okay, so let's try a few practice problems. So again, remember to start off with identify whether the first element is a metal or a nonmetal, and that'll tell you whether it's ionic or covalent. Our first problem is CaF2. So for this one, when we look at Ca, calcium, that is a metal found in group 2. So therefore, we know it is going to be a type 1 ionic compound. So for these, we just simply list the name of the metal, calcium, and then we add the ending IDE to the nonmetal, calcium fluoride. Our second example is K2S. So for K2S, again, we have potassium being a group 1 metal, and then that would mean no Roman numerals, sulfide to finish it off. Next we have COI2. We still have a metal, cobalt, but now cobalt is listed in the middle section. You should find cobalt in group 9. And we would have cobalt. In this case, because it's COI2, I need to determine the charge for the cobalt. And since the iodide ion is a 1- charge and there are 2 of them, total of 2- for the charge, so therefore the cobalt must be a +2 for the charge. So in this case, I would have COI2 being cobalt 2 iodide. Now, just so you can visualize that once more, again, we don't know the charge on the cobalt, but I know that each one of the iodide ions has a 1- charge, so altogether they have a 2- charge. So in order for those to cancel out to equal 0, I know that the cobalt must be a +2 charge. Our next example is SnF2. Sn is tin, and it is also another metal that can be able to have 2 different charges. So in this case, I have tin. Same thing. We're going to do Roman numeral 2 since F has a -1 charge. And then we would finish off with fluoride. Now we look at another example using tin, but this time we have 4 fluorines instead of just 2. So for this one, we know that tin must have a 4+ charge. So I'd have tin 4 fluoride. Excuse me. Our next example is OF2. So now in this case, notice that the oxygen is a nonmetal, so therefore instead of an ionic compound, we now have a covalent. So once more, we write the name of the first element. So we would have oxygen, and now my prefix for 2 is di. So I would have oxygen difluoride. For our next example, we have CuI2. So in this case, we have copper. Roman numeral 2, and iodide. Our next example, CuI, Once more, we still have copper, but now we have a 1-to-1 ratio with copper being a -1 charge. So we have copper 1 iodide. And I believe our last example on this slide, we have SO2. Once more, the S is a nonmetal, so that means that this will be a covalent compound. So we would write sulfur for the name of the first element, and prefix of di for 2, and oxide. Oh, one more to go. So with this one, SRS, SR is a metal. It is located in group 2. So this will be one of our type 1 ionic compounds. So when we write the name for this, we would simply write strontium. Sulfide. And now for our last example. Li, that is lithium, group 1 metal. And bromide. Now we're going to focus on acids. Acids will always have a hydrogen plus some type of anion. Now, depending on the type of anion, we have a different set of rules, which can be confusing, but I'm going to show you a little way to work it where it should hopefully remove the confusion. So when we're talking about your anions, we have two different types of acids that we can use. We have a binary acid, which is just hydrogen plus a nonmetal. So you're going to have only two types of elements present. And then we have what we call ternary acids, which will also be called oxyacids because they contain polyatomic ions which have oxygen present. So you'd have hydrogen plus a polyatomic ion, which I abbreviate as PAI. So now, when we look at the rules, I'm going to give you 3 simple sentences for you to memorize that depend on the ending for the anion. And if you can remember these 3 sentences, you can name any acid that's given to you. The first one that we have is my ride has hydraulics. So for these, we're always talking about the ending of the anion. So again, anion ends in this case, IDE. And for those that have the IDE ending, we use the hydro prefix and the IC suffix for our acids. So in a case like this, if I gave you something like H2S, I would use, in this case, because the S is sulfide and ends in IDE, I'm going to use the hydro prefix and the IC acid suffix. Okay, so my ride has hydraulics. And now for your polyatomic ions, the first sentence would be for your binary. For your 2 polyatomic ions, you can say I ate something fantastic. So the polyatomic ion, your anion, ends in ATE. You can simply add IC acid. So an example for something like that would be HNO3. The NO3 polyatomic ion, if you remember, is nitrate. So I'm going to replace the AT ending with IC acid. No hydro prefix is used. So I would just have nitric to replace the ATE ending, acid. And finally, for your ITE ending polyatomic ion, Sprite is delicious. So when you have an ITE ending for your polyatomic ion, you drop that ITE and you add OUS. So if I gave you H3PO3, the PO3 is the phosphite ion, so I would call that phosphorus acid. Okay, so let's try a few practice problems naming acids and writing their formulas. So in our first one, we have H2SO4. You'll hopefully notice this compound has more than 2 elements, therefore it is one of our ternary acids or oxyacids. So when I figure out the name for this, I need to focus on the anion. SO4 is the sulfate ion, and therefore we're going to change the ending of this to IC. Phosphate and sulfate compounds, anything with sulfur or phosphorus, they have a little bit of a unique change where it will actually add back on the UR or the OR just for phonetics, because it sounds better to say sulfuric acid than it does to say sulfic acid. So in this case, again, no hydro prefix. So I'm going to add back on the UR, so I'd have sulfuric acid. In our next example, I have HCl. In this case, we only have 2 elements present, so this would be a binary acid. So when I look at the Cl, that is the chloride. So in this case, I'm going to use the myride has hydraulics. So I would have hydro as our prefix, and then the chloric acid. We never have to name the hydrogen. It's always understood that it's there based on the fact that it says acid. When I now look at the third example, HCN, this one has 3 elements present, so it does have a polyatomic ion. However, it does not have oxygen, so it is not technically an oxyacid, and so we're going to name it differently. This polyatomic ion, CN, is cyanide, so it is going to also look like our binary acids because it ends in IDE. I am going to use the hydro prefix, and then I would have cyanic acid. Now, the reason for this is because we have another polyatomic ion very close to it, which is CNO-, and this is the cyanate ion. So if I had HCNO, because it ends in ATE, that one will be called cyanic acid. That's why we had the differentiation with this one, and we put the hydro prefix in front. For our last compound, we have HClO2. The ClO2, that is the polyatomic ion chlorite. And so we're going to use the Sprite is delicious formula there. And so I'm going to take off the ITE and add OUS acid. So I'd have chlorous acid. Now, if we transition to the other side, here's where we want to use our rules for writing formulas. Acids are going to be treated just like ionic compounds, so we're going to always be looking for charges that are found between the different ions. So again, because I have the acid present, I always would have a hydrogen ion, which is going to be H+. And now I'm going to use those 3 sentences to kind of reverse engineer to figure out which anion we are using. In this first example for acetic acid, notice there is no hydro prefix. Therefore, I know it is a polyatomic ion. Since it ends in IC acid, I know that the polyatomic ion must end in ATE. So that means that I now have the acetate ion, which off of your polyatomic ion list is C2H3O2 with a 1- charge. Now, because I have a 1+ and a 1- charge, the acetic acid formula will therefore be HC2H3O2. It is important to keep the hydrogens separate from each other because later on, when we start talking about acid-base chemistry, we'll know which one of the hydrogens will actually separate when they dissociate or ionize in water. So please keep them separate. When we look at our next example, hydrobromic acid. In this case now, because I do see that hydro prefix, I now know this is a binary acid, which means that my ending for my anion will be the IDE. So I would now have bromide as my anion. So I would have H plus, bromide means that it's coming from the periodic table. Bromine again is in group 17, so I would have Br minus, and so I'd have a formula simply HBr. The next example, nitrous acid. Again, there is no hydro prefix, so therefore I know it must be an oxyacid. And so when I see the OUS, that tells me that it is the ITE ending, so that would mean that I would have the polyatomic ion nitrite. Nitrite is NO2, 1 minus. One plus, 1 minus, so therefore they will cancel out, and I would just have HNO2. And finally, our last example is arsenous acid. Once again, because it is ending in OUS and there is no hydro prefix, I know that will be the polyatomic ion arsenite. And arsenite is AsO3 with a 3 minus charge. So having H plus and AsO3, 3 minus, that will give me a formula of H3AsO3. One easy way to remember how to form these compounds is the number of hydrogens, because it's always a 1 plus for hydrogen. The number of hydrogens will always match the charge of your anion. So if you look back at each one of these examples, 1 minus, 1 minus, 1 minus for the first three, notice that there's 1 hydrogen in each of the acid formulas. When we come to the H3ASO3, again, arsenite has a 3 minus charge, so I have 3 atoms of hydrogen in the compound. So here's a really good example of a typical type of multiple choice question that you would see on your test. Which of the following compounds is named incorrectly? KNO3 potassium nitrate, TiO2 titanium 2 oxide, SnOH parentheses 4 tin 4 hydroxide, PBr5 phosphorus pentabromide, and finally H2SO3 sulfurous acid. So as we look at the first problem, we have potassium as K, and that is correct, and we have nitrate, which is NO3, both 1 plus and 1 minus, so KNO3 is the correct formula for potassium nitrate. When we look at TiO2, once again, everything at the beginning looks like it is fine. However, what you need to remember is to always check the charge of your anion. Going back and finding oxygen, you notice oxygen is found in group 16, which means that it has a 2 minus charge. So each of those compounds, or each of the oxygens in that compound, would have a 2 minus charge. Therefore, it would have a total of -4. So that means that the 1 atom of titanium must have a 4 plus charge for everything to cancel out and add up to equal 0. So B would be the correct answer choice with this. You can do the same thing for the next 3 just to make sure. The tin 4 hydroxide, again, each hydroxide has a -1 charge. There are 4 of them. So I have a total of 4 minus, so therefore the tin has to have a 4 plus charge. So that is correct. For phosphorus pentabromide, this is a covalent compound. Therefore, it would use the prefixes. Penta is the prefix for 5. There is not a prefix necessary for the phosphorus since it has only 1. And finally, as we were just looking at, for H2SO3 being sulfurous acid, the polyatomic ion SO3, 2-, is the sulfite ion, which would change to the OUS ending. So you can go through and eliminate the choices from that. So titanium 2 oxide should more correctly be written as titanium 4 oxide to be correct. Okay, so we finally hit the point where we're getting to new nomenclature that probably no one has done before. You guys were introduced to the very basics of naming organic compounds last year, but now we're going to get into the more complex branched hydrocarbons instead of just single straight chained compounds. So to start off with, just for definitions here, the hydrocarbon is a compound that consists only of carbon and hydrogen. They're grouped based on the number of bonds between the carbon atoms, and they are named based on how many carbon atoms are found in the main chain. We have 4 basic types of hydrocarbons. We have alkanes, where we have nothing but single bonds, so all carbons are singly bonded. So remember, all carbon atoms can form a total of 4 bonds. With your alkenes, that means that you have carbons that can be double bonded as well. So not all of them will have a double bond, but you'll have at least one double bond within the structure. An alkyne is a hydrocarbon where the carbon atoms, at least one, will contain a triple bond. Now, if you don't remember from our bonding unit last year, a single bond means that there are 2 electrons being shared between 2 atoms. That would be your sigma bond. You have a double bond, which was a sharing of 4 electrons between 2 carbon atoms. And finally, for a triple bond, you have 6 electrons being shared between the carbon atoms. Now, you can represent those 2 shared electrons as just a single dashed line. So if I had a alkane, it would have a single bond that was present. If I had an alkene, it would have a double bond, so it would have 2 lines being shown between the 2 carbons. And finally, a triple bond would have 3 lines that are shown. Now, in terms of these alkanes, alkenes, and alkynes, we have a general form which you can look at to figure out what type of compound it is. So for an alkane, it would have the simple formula of CnH2n plus 2. So in a case like this, the N represents the number of carbon atoms. They're going to have a different set of prefixes that we will go over shortly, which will tell you the name that we would put in front for the prefix, and then we would add the ANE suffix. When we look at an alkene, it is going to have a general form of H2n, so CnH2n. And finally, for your alkynes, we would have CnH2n minus 2. Now, the last type that we have are called aromatic hydrocarbons. And when you have an aromatic hydrocarbon, you have alternating single and double bonds throughout the structure. So if you had a compound that looked like this, notice I have an alternation. Every other carbon in the compound had a double bond. That would be an example of an aromatic hydrocarbon. Now here is a list of prefixes that you will need to memorize for organic chemistry. These are the first 10. Again, notice in each of these they have an A-N-E ending. That will not always be the case, but in this one particular example, these are all singly bonded carbon atoms, so they're all ending in A-N-E. So your prefixes for one carbon, you use the prefix meth. For 2 carbons, it is eth. For 3, you use prop. 4 is bute. 5 is pent. 6 is hex, 7 is hept, 8 is oct, 9 is non, 10 is dec. So it's only really the first 4 that are very different from the covalent prefixes. But again, instead of mono, we're going to use meth. Instead of di, we use eth. Prop for 3, but for 4. So you probably have gotten familiar with a couple of these. Propane is what we use in our gas grills. Butane is used in cigarette lighters. Hexane is a very commonly used organic solvent in the lab situations. So you're going to be using these different prefixes here when you're naming your compounds. Okay, so I wanted to show you first just a couple of common methods that we use for writing structures in organic chemistry. Structural formulas are going to show how all the atoms are bonded to each other. This by far is the most tedious way to show an organic compound because you have to write out all of the different H's connected to each of the different carbons. And so that takes a lot of time. So instead of doing that, sometimes we use what's called a condensed structural formula. So instead of showing out the C individually bonded out to all 3 of the different hydrogens, we just write CH3 or H3C depending on where the carbon is located in the chain. So this way we don't have to write all of the different hydrogens out connected to the carbons, but we can still denote how many hydrogens are present with that one particular carbon. So if you remember, every single carbon must have a total of 4 bonds. So when you look at this bottom structure right over here, you can always assume, since there's nothing but carbons and hydrogens, that each of the different carbons has a bond between them, just like you see over here. So if you notice here, I have CH3, and if you notice over here, I have a CH3. I have a CH2 and a CH2. Notice here, CH2, CH2. So I have 2 different CH2s, and then I end with another CH3. So it's just another way that you can write a formula for or a compound. Just makes it a little bit faster. Now, by far, the fastest way that we can do this is something that we call a line angle formula. And you can see that denoted in the structure 4 down here, where instead of listing out any type of carbon or hydrogen, all we do is show the carbons or any other elements that are attached to them as a line. And when the line changes direction, that's a new carbon. So if I were going to look at this butane structure, the actual way how it would look would be like this. I'd have C, 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 C. So again, every time that I have that break in the line, I'm going to just change the direction. So I'd have carbon 1 here, carbon 2, carbon 3, and carbon 4, just like I have right here. So now the great thing about this line angle formula, all the hydrogens are assumed to be attached to the carbons. So all you have to do is look at how many of the carbons are bonded to another atom. And then again, the magic number for the carbons is 4. So that's how many hydrogens you would add. So when you look at carbons 1 and 4, each of them are only bonded to one other carbon. And so each one of these would have 3 hydrogens. When you look at carbons 2 and 3, each carbon is bonded to 2 other carbons, so therefore there would be 2 different bonds for the hydrogens. And you'd see that on carbon 3 as well. So carbon 1 and carbon 4, you would see 3 different hydrogens bonded to it, whereas carbons 2 and 3 would only have 2. This is by far the easiest method that you can use, most time efficient, to write out the formulas for the compounds. Now, this last compound, again, this is what we would call having a functional group on it. Notice I have an oxygen present, so it still is a hydrocarbon, but because it's got an oxygen present, we would name it differently. So this one here, since I have that double bonded oxygen, that's actually what we would call a ketone. You won't learn about that until the very end of the year, so don't worry about that now. Okay, so once again, let's look at how we're drawing out this line angle formula. So as you look at this structure, first off, we have 1, 2, 3. I'm going to label these 1, 2, 3, 4, 5, 6, 7. So as practice, let's go ahead and name this one really quickly. Since I have 7 carbons, that would be the prefix hept. And if you notice, every single carbon is nothing but single bonds. So I'd add the ane for the heptane. Notice I have 3, 5, 7, 9, 11, 13, 16. So I have C7, H16 for the formula, 2N plus 2. So that makes it an alkane. So now, as I'm drawing this line angle formula, again, every time I have a new carbon, it changes direction. So I'd write my first bond here. This would be carbon 1 and carbon 2. Then I would have carbon 3, carbon 4, carbon 5, carbon 6, and finally carbon 7. Hopefully you can notice it mirrors the shape that we see for the compound with the hydrogens included in that structure. So now we're going to learn how to name branched hydrocarbons. In the first few examples, we were using straight chained hydrocarbons. Now we're going to have branches that are going to be coming off of that main chain. We call the branching a substituent group. When we have a substituent group, we're going to change the name. Instead of saying that it is ethane, we're going to drop the ending and we're going to add a YL. So if I had a C2H5 group coming off, 2 carbons would be eth, so we would call that an ethyl group. When we look at the base, that is for the longest continuous chain of carbons. How many do we have? So that's again where we're using our meth, eth, prop, bute, penta, so on and so forth. And then finally the suffix for what family, that again, does it end in ane, does it end in ene, or yne? So is it an alkane, an alkene, or an alkyne? So again, to determine that, we're going to look at the type of bonds that are connecting the carbon atoms together. Now we're going to get into how we actually name the compounds, getting through the list of rules. The very first and most important thing to do is to find the longest continuous chain of carbon atoms, and we'll use that for the base name. So when we're doing this, please remember there is a 360-degree freedom of rotation for any single bond. So therefore, notice here we arbitrarily chose this as carbon number 1. It's attached to carbon number 2, and notice that there's a branch group that is coming off of carbon number 2. Now, with that branch group, we could have just as easily had made this carbon number 1, 2, 3, 4, 5, 6, and still had the branch coming off of carbon number 2, and it would have been the same exact thing. So the most difficult part for this is going to be determining the longest continuous chain and then start your numbering system. Now, notice with this branching that occurs here, I have 1 carbon that's involved in that branch. So it's going to get the meth prefix, but again, instead of saying methane, we're going to drop that ane ending and we're going to add YL. So this part right here, that is our methyl group. And we also need to tell where on the compound it is branching from. So when we do this, we could number it in either direction, but we want to always number the chain, the longest continuous chain, so that the branch that's coming off gets the lowest number, which we call a locant. So that 1 or 2, that is called a locant. So in this case, because it's coming off of carbon 2 going in this direction, if I numbered it going from right to left, I'd have 1, 2, 3, 4, 5, and 6. So I'd have 5 where I'd see the ethyl or the 2. Since 2 is lower than 5, we would name this 2-methyl, and I have 6 carbons all singly bonded, so I have hex, and then I have the ane ending to represent the fact that it is an alkane. So I'd have 2-methyl hexane. All of these are one entire word. So that's one of the things that's going to be kind of weird, especially when we get multiple branches. Some of these names are going to get really, really long. So again, name your substituent group based off of how many carbons are coming off of the main chain, and add the YL ending. As the number of substituent groups or branches continues to increase, it becomes more complex. So what you need to do is number the longest continuous chain in each direction. When you're doing this, the best thing to do is to put a box around each of the different branched groups where you have them, and then begin to tell where their positions are. When you have more than one substituent group that is a different type of substituent group, you're going to list them alphabetically for priority. So in this case, it doesn't matter where they come on the chain, we're just going to list them alphabetically. So in this first example where I have CH2, CH3, I have 2 total carbons that are branching off of that chain at that particular spot. So this would be called an ethyl group. Notice here I have 3 different CH3s. Each one of those, because it has just one carbon branching, that is what we would call a methyl group. When we have more than one of the same substituent group that are branching off the chains, we would then go back and use the typical covalent prefixes, di, tri, tetra, to list out the number for each of those different substituent groups. When we do this, we place the number for the substituent group, we put a dash, and then we list the substituent group for where it's located on the chain. So you'll notice in this first example, I have 1, 2, 3, 4, 5, 6, 7. So I have on the 3rd carbon, I have an ethyl group coming off. So I put the 3 with a dashed line, and then the ethyl. It can be capitalized, it doesn't have to be. And then notice here, because I have 3 different methyl groups, I put trimethyl. But I also have to list each position where those methyl groups are found. So I have a methyl group coming off of carbon number 2, a methyl group coming off of carbon number 4, and a methyl group coming off of carbon number 5. When we're doing this, as far as figuring out which way we want to number, again, we want to give it the first substituent the lowest number possible. So if we numbered it going from top to bottom, I'd have carbon 1, 2, 3. So my first branching would occur at carbon number 3, versus on the bottom, the branching occurs first at carbon number 2. That is why we numbered it from bottom to top in this particular instance. When a compound contains a double bond, it is necessary to tell the position of the double bond within the main chain as well. So when we look at the first few examples here, notice we have a 5-carbon chain with a single double bond. So for this, we know that this compound would be called pentene. However, there can be many different positions for that double bond, so we need to be specific about where the double bond occurs. So we would list with a number out in front where the double bond first starts. So in this case, because the first example, I have the double bond appearing between carbons 1 and 2, I would call this 1-pentene. When we looked at the second example, now notice the double bond is between carbons 2 and 3. The lowest number that we can give to the beginning of the double bond is a 2. So this would now be 2-pentene. When we look at the third example, now notice, again, I have the first double bond going between carbons 3 and 4 if we're solely numbering from left to right. However, if you were to look at this from the other direction, you would notice that the numbering from right to left, the first carbon containing the double bond is carbon number 2. So this structure here is actually the exact same structure as the one above it. And then same thing, if we look at this going from left to right, it would appear as if we would have 4-pentene, but if we number it going the opposite direction, we would actually have 1 pentene as well. So you have the ability to place the prefix out in front. A more modern way that you're seeing it done in organic chemistry classes is to also put the prefix first, then put the position. So I'd have pent 1 and then add the ene to represent the double bond for an alkene. Either way for me is perfectly acceptable. If you have more than one double bond that is present, then just like when we have multiple substituent groups, we're going to use those prefixes, di, tri, tetra, so on and so forth. So if I had a structure that looked like this, where I have 6 total carbons, now you'll notice here that I have numbering from left to right, carbons 1, 2, 3, 4, 5, and 6. If I number from right to left, I'd have carbons 1, 2, 3, 4, 5, 6. So in this particular case, it does not matter which direction I use to number it because my carbons are both coming off on 2 going in either direction. So in a case like this, I could put 2, 4, because again the other set is coming off on carbon number 4. I could have 2, 4, and now the dash. I have 6 total carbons, so that would be the hex. Now for this, I'm going to add back in the A, and now because I have 2 double bonds, I'm going to use that di prefix, and then I'm going to use the ene suffix. So I'd have 2,4-hexadiene. Or we could also do hexa 2, 4 diene. So just remember, with chemistry, if you're not trying, you're dying. So when we go on to our next slide, we're going to begin to look at the different names for some of the common substituent groups. Okay, so here's some commonly used alkyl groups. Remember, the alkyl group is just the alkane that has been attached as a side chain. So again, a CH3 with a dash, that is your methyl group. A CH3CH2 is an ethyl group. You'll notice with each of these that it has one less hydrogen compared to what the normal alkane would be. Methane would be CH4, again CnH2n plus 2, but we're having to remove a hydrogen in order to connect it to a carbon on the main chain. That's why it's dropped by 1. So instead of CH3CH3 for the ethane, the ethyl group has just CH3CH2. So when you get down to these bottom 2 over here, these are some more advanced ones. The prefixes that you see in the front, such as the iso, you may recognize that as like isopropyl alcohol. The iso is telling us where the main chain attaches to the carbons within that substituent group. So you'll notice with the propyl group, the attachment comes on the very end carbon. With a isopropyl, it's attached to the second carbon, the middle carbon in the chain, so it would be attached to this carbon instead. And that's the only thing that's different that makes it an isopropyl group. It still has, if you count, C3H7, C3H7 for that propyl group. So it's just depending on where the attachment occurs. Now we're going to look at cycloalkanes. Anytime that you see that cyclo prefix, that tells you that you have a ring structure for that particular compound. The way how these are formed is we're going to take one of the hydrogens off of each end of the hydrocarbon chain from each of the remaining carbons, and we're going to connect the 2 carbons together. So if you notice down here on our first picture, I have cyclohexane, where each of the different carbons is connected to 2 other carbons. So each carbon has 2 hydrogens bonded to it. The way how this was formed was to take a hexane molecule, where the two, we call them terminal carbons because they're the end of the chains, have 3 hydrogens. Each of the interior carbons has 2 hydrogens. And so what you'll see happening is they're going to remove 2 of the outer hydrogens. So now each of these exterior carbons will have only 3 other bonds to hydrogens. And we're now going to make a bond between these 2 carbons. And that gives it this ring structure that we see. Okay, so now if we had cyclopentane, you have again the 5 carbons, each with a CH2 group there, that are all attached together. We can have cycloalkenes. If we did have a cycloalkene, it would just have a double bond present somewhere within the molecule. Typically, when we look at your cycloalkanes, your 5 and 6 membered rings are the most common because they give an appropriate bond angle for that sp3 hybridization that we'll talk about in a long time. When you get down to something like the cyclopropane or cyclobutane, now you have a very unstable molecule because of the fact that the bond angles are so much different than what they should be. So instead of having a 109.5 degree angle, now you're talking for cyclopropane having a bond angle around 60, or if you have butane having a bond angle around 90. So very far off from the desired bond angle, and so therefore it is not very stable for that compound. So as far as naming is concerned, it works just the same way as we have for the normal alkanes, except that you would add a cyclo in front of the name. If you have any substituent groups coming off of them, you would number those as well. If it is just one substituent group, you don't have to actually put a number because there's no starting point and ending point. You would always give it the 1 for the prefix. If it has multiple substituent groups, then you want to name it in the direction that gives the lowest number for your locants, or the positions where those substituent groups are coming off. We'll do a couple of examples here in just a minute where you can see what we're talking about. Okay, so let's go through a couple of examples for some branched cycloalkanes. So in this first example, we're going to do a 6-membered ring. Please remember that each branch that is going off in a different direction, or each line in a different direction, represents a carbon. So I have 1, 2, 3, 4, 5, 6 different carbons. And I'm just going to make this simple, and I'm going to put one substituent group here. This substituent group has 2 total carbons. So again, we would take the ethane, drop the ending, and add YL. So I have an ethyl group that is present. So for my naming, because there's only one substituent group, and again, there's no beginning or end to the main chain, I do not have to use a prefix out in front. So in this case, I would just call this ethyl cyclo to represent the ring, and there were 6 members in that ring, all single bonds, so I'd have ethyl cyclohexane. Now let's look at an example where we have 2 substituent groups that are coming off of a chain. So in this case, I'm going to now have a 5-membered ring. I'm going to use again a substituent group with 2 carbons, but I'm also going to use a substituent with 1 carbon. So now, again, I'm going to call this an ethyl group. With the 1 carbon here, this would be a methyl group. You're not combining them together and calling it propyl. You would keep each one of those separate. So in this case, now for numbering, I could go 1, 2, 3, 4, 5, or I could also go 1, 2, 3, 4, 5. So I want to number it in the way that gives the lowest possible numbers. So I'm going to use the 1 and the 3 since 3 is lower than 4. I always start it with the substituent group in this case because I have only 2. I'm going to start with the one that has the lower alphabetical order. I could have started with the methyl group as 1, but because there's just 2 of them, ethyl will take the priority. So in this case, I would label this as 1 ethyl, and then I would have 3 methyl, and finally cyclo, and I have a 5-membered ring, so that would be pentane. So again, when all things are equal in terms of the substituent groups, then we're going to number it based off of the alphabetical order. The lower alphabetical order takes the priority. E comes before M, so it will go first. Now let's look at one other example where you can see an example of where that will not happen. We're now going to have a 3-membered ring, or a 3 substituent group compound, and I'm going to start off with an 8-membered ring. So this would be called cyclooctane. Should look hopefully kind of like a stop sign. But now I'm going to put 2 different methyl groups coming off of the same carbon. And then I'm also going to put an ethyl group as well. So I have 1, 2 here, so that would be your ethyl group. And now I have 1 carbon and 1 carbon, so I have a substituent group here. And here. Now, when we write this out, again, giving it the lowest set of numbers possible, if I were to start with the ethyl group as the first carbon, I'd have 1, 2, and 3. So I'd have the first branch coming off for the methyls both at 3. So that would give me 1 for the ethyl, and then I would have 3, 3 dimethyl cyclooctane. Now, the problem with this, however, is if we name it in the other direction, where I put this as carbon 1, 2, and 3. Now notice in this example, I would have 3 ethyl, and then I'd have 1, 1 dimethyl cyclooctane. So in this third example, you'll notice that by numbering it with the bottom direction, going from the methyls as the 1, my overall set of locants is lower, and so the correct answer would now become the bottom. So in this last example, it doesn't matter alphabetical order, and please remember that the D does not count towards alphabetizing. So just still be the M versus the E, but because of the fact that I have 2 methyl groups, we can then prioritize both of them coming off of the same carbon, being carbon number 1. Okay, so we've gotten through all the rules, so now let's just look at a couple of examples to make sure that we have everything figured out. So the very first step, if you recall, identify your longest continuous chain. So in this case, I have carbons 1, 2, 3, 4, 5. Going over from this direction, I'd have carbons 1, 2, 3, 4, 5. So everything, no matter which way I go, I'm going to have 5 carbons in the longest continuous chain. So now, once we have that, we need to determine, do I need to go from top to bottom, or do I need to go from bottom to top? Again, to determine how we do that, we look at the substituent groups that are coming off. So I have a substituent group here, I have a substituent group here, and I have one here. Now in this first particular example, you'll notice that in either direction that we go, I've got one coming off of carbons 2, 3, and 4. So for the naming for this, I'd have 2, 3, 4. Notice each of my substituent groups are just a CH3 or a methyl group. So I would now have tri to show that I have 3 different methyls. And then I have a 5 carbon chain, so that would be pentane. Okay, so if we now look at our next example, we're going to do the same thing. We need to identify the longest continuous chain. So just to start off with, I'm going to go 1, 2, 3, 4, 5. That's definitely part of the longest chain here. Now, if I go down, it would just be a 6-membered chain, but if I go up, I could have 6 and 7. So I now have a 7-membered longest chain. So I'm just going to put a box around that. So in this case, I know that I have a heptane. And now if you notice, I have 2 different substituent groups, both being CH3s. So now, in terms of my numbering, notice the first branching occurs on carbon number 5, going from right to left. But if I go from left to right, this would be carbon 1, this would be carbon 2. So in this case, I would have my first branch coming off on carbon number 2. So I'm going to number it going from left to right. So in this case, I'd have a branch on carbon number 2 and a branch on carbon number 3. So I'd have 2, 3 to represent my 2 methyl groups. I have present, I would say dimethyl, and because I have a 7-carbon continuous chain, that would be heptane. So I have 2,3-dimethyl heptane. So for our next example, we have a tricky looking compound, but it's really not actually that bad once you identify all the pieces. So the first thing that we need to do is identify our longest continuous chain, which would be right here. It contains 1, 2, 3, 4, 5, 6, 7 different carbons. So now we need to identify our different substituent groups. So I have a substituent group coming off here, here, and here. They are all methyl groups. So once again, we have a trimethyl situation. We need to figure out our numbering for it. So as we start this off, if we number going from right to left, this would be carbon 1, 2, 3, 4, 5, 6, and 7. So our first substituent group we find at carbon number 3. Now if we go in the opposite direction, carbon 1, 2, 3, 4, 5, 6, and 7, once again, we have the same issue. I still have 5 and 3 for the positions, but we need to give us the one that provides the lowest set of numbers. So in a case like this, we want to start from the carbon on the left and count to the right. So now my 2 substituent groups coming off of the first carbon are on the 3rd carbon in the chain. And then I have 1 coming off of carbon number 5. If we went from right to left, I'd have 1 carbon coming off of 3 and 2 coming off of 5. So instead of having 3, 5, 5, we're now going to have 3, 3, 5, trimethyl, and then heptane. Okay, so in this example we have a very long hydrocarbon. So again, first thing is to identify what our longest continuous chain would be. So I'm going to start over here on the left once again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have a 10 carbon chain, and I have a methyl group coming off of this carbon, and a methyl group here, and an ethyl group. So please remember, even though these 3 carbons are coming off of the same carbon in the main chain, because they are not connected together, they are 2 separate substituent groups. So in this case, I have 2 methyls and 1 ethyl group, so I'm going to put the ethyl first, and then I'm going to put the 2 methyls on after that. Numbering wise though, I would have 7, 7, and 9, or if I number going in this direction, I would now have a much lower set going from right to left, and I would have 2 and then 4 and 4. So in this particular example, I would have 4 ethyl, a dash, 2,4 dimethyl, and then decane. Okay, so 4-ethyl, 2,4-dimethyl decane. So for this example, we now have our first alkyne involved. Remember, an alkyne has a triple bond. You can see the 3 different lines representing the 3 shared sets of 2 electrons each. Now, for this, same thing, we're going to start off by finding our longest continuous chain of carbons. In this case, we'd have carbons 1, 2, 3, 4, 5, 6. So we have 6 carbons total in our longest continuous chain. Now, here's where the rules get a little bit different. When you have double or triple bonds that are present in a compound, they get the highest priority compared to the regular alkyl substituent groups. So automatically, does not matter where my 2 substituents are located on the chain, we are going to start numbering. And actually, I'm going to do this smartly and change colors. Sorry. 1, 2, 3, 4, 5, 6. So now automatically carbon 1 and 2 are the 2 that are involved in the triple bond. So I now have 2 different methyl groups, each one coming off of carbon number 4. And so this one would be named 4,4 dimethyl. And then remember, we have to tell the lowest position where the double bond or triple bond starts. So then I would say 1 hex, and then because it's a triple bond, the suffix would be YNE. So 4,4 dimethyl 1-hexyne would be the name of this compound. All right, mercifully, we're on our last one. So thank you for hanging in there with me. So in this case, we now have a cyclo compound. Notice that I have a total of 4 members within the ring. 1, 2, 3, and 4. And then I have 1 substituent group coming off of it. So in this case, because there's only 1, please remember you do not have to actually add in the prefix for the number. So in this case, we would just have methyl for our CH3 group. And then I'd use the cyclo prefix. I have a 4-membered ring. Each one is a single bond. 4 would be bute, and ANE for the ending. So methyl cyclobutane. All right, so that concludes this first presentation. I appreciate you hanging in there with me for it. Please come to class with questions tomorrow on things that you don't understand, and we'll do a lot of practice. Thank you. Good night.